This is section 4.7, optimization, and our first and only objective is to solve optimization problems. This section, like the related rate section, will require you to read and interpret story problems. The overall goal is to maximize or minimize a quantity that's presented in the problem. For the majority of these problems, I will allow calculator usage. And to complete the problems with the calculator, you will need to follow these 7 steps. So rather than have me read them all to you, I would like you to pause the video and read them in your notes, steps 1 through 7. We're going to do each of the 4 examples as if we do not have a calculator. So we're going to show all of the work that would be required even if we do have a calculator on any free response problem given by the AP test. So that means we need to go through all of our steps and we need to show all of the analytical work properly, and then we'll use our calculator as a backup and to help us find zeros. So with example 1, we want to find 2 numbers whose sum is 20 and whose product is as large as possible. So our first step is to read it carefully and understand what is given and what is wanted. So we're given 2 numbers whose sum is 20, and we want the product of those numbers to be as big as possible. Step 2 of that process is now we want to come up with a model, and that model looks like a function of the form where we have the maximum or minimum variable equaling something in terms of one variable. Now, because we have a calculator available, we want to always let that one variable be x because it makes it much simpler for us to plug into the calculator. So what we're going to do is we are going to write down the relationships that we have and then the relationship that we want. We have 2 numbers whose sum is 20, and we're going to let one of them be an x. We're interested in the product being as large as possible. So the product is those 2 numbers multiplied together. Our goal is to get to the thing that we want to maximize, which is the p, and get it written in terms of that single variable x. So to do that, we're going to have to get rid of the y, and that's where the other relationship comes into play, because we know that we can solve for y and get a 20 minus x. If I substitute that in, now I have a function for the product that is in terms of x only. We also want to keep in mind what the constraints are on these variables. Looking right now, I can take any 2 numbers, and as long as they add up to 20, they're viable. But the goal is to get a product that's as large as possible. So it would not make sense to be entertaining negative numbers because everyone knows that positive numbers are larger than negative numbers. So that means neither x nor y could be negative, because if they're both negative, then we won't get a sum that is 20. So based on that, we can say that x and y will both need to be bigger than 0. If we move now to step 3, this is the calculator portion. So on step 3, we're going to let y1 equal this function. So we're going to hold off for a second. We won't put that in because we're going to go through a few more steps. Step 4 is we want to identify that function's domain. Because we have the function written in terms of x, that means we're looking for limitations on x. Well, we've got that x has to be bigger than 0 already. So what we want to do now is think about what that upper limit on x is going to be. Because y is also positive, then the smallest that y could be was 0. That would mean that x will equal 20, and that's the biggest that x can be, because if y gets larger, then x is going to shrink. So here we've got our domain, and we can use it when we graph our derivative. So step 5 is the calculator step, and we want to support it analytically. So analytically, if we're trying to maximize things, we want to take the derivative and set it equal to 0 or undefined. So if I take the derivative of this, I get a 20 minus a 2x, and I'm interested in knowing when that derivative is 0 or undefined. We can see that it's never undefined, and we can see that it is 0 when x is 10. Step 6 is to draw our sign chart for p prime. Now in this particular case, it's pretty simple because we can put on our domain from 0 to 20, and we can put that 10, and we can see that prior to 10, say at 1, we're going to get a positive number, and after 10, we're going to get a negative number. Based on this, I could now go to step 7 and I could summarize very readily. We can write down that p has a max of 10 plugged into P would give me 200 minus 100, which is 100, when x equals 10 and y equals 10, because P is continuous and P prime changed from positive to negative. Now I'd like to show you how the calculator can be used to support everything that we've done analytically here. If you look at the calculator here, you can see that I put my original function that I want to maximize into y1, and I put the derivative of that function, letting the calculator do the work, into y2, and now I'm going to turn off y1 because I'm interested in graphing just that derivative function. I want to know when is it above the x-axis and when is it below the x-axis. So to do that, I want to make sure that I use the domain of the original function so that I'm looking in the right place. So if I go to my window, we can see that I've used the domain from 0 to 20, and then I'm going to do my ymin and ymax, just ensuring that I straddle the x-axis, because I'm interested in when x is positive and when when the derivative is positive and when the derivative is negative, and when it crosses the x-axis. If I graph this, I should see a sign chart for P prime with more information attached. Notice we can see that P prime is above the x-axis, then it's 0 at 10, and then it's below the x-axis. So that would support what we saw here as our sign chart. In order to get this max value out, I could on the home screen do y1 of that x-intercept, and I would get 100, which is what we had here. With example 2, we have a rectangle that is going to be inscribed under one arch of the sine curve, and the goal is to find the largest area of that rectangle and the dimensions that give that area. So if we read this carefully, which is step 1, we can see that we're trying to maximize the area of this green rectangle. So I've already started step 2 for you by drawing this picture. We have one arch of the sine curve, and underneath that sine curve we have built a rectangle. Our goal is to get the largest area. So when we're done, we want to have area in terms of a single variable. Well, right now we know that the area of a rectangle is a base times a height. Our goal is to get that area in terms of x. So we have to decide on our picture what this x is going to represent. What we know is that on the coordinate plane, x represents an x coordinate, and that is in turn the distance from the origin horizontally to the point that you're trying to graph. So we have to decide whether we want to stop here or stop here. And a general rule of thumb is you want to let x move to the right from the origin until it hits an edge of whatever shape you've drawn. So in this case, our x would represent the distance from the origin to the left edge of this rectangle. Now once we have decided that that is our x, we have to now figure out what the base and the height of that rectangle are in terms of x. So to get the base, we're going to use the symmetry of the sine curve, and we're going to see that since the sine intersects at 0 and then again at pi, and we've got symmetry along the center of that arch, we can see that if this is x, then this piece over here will also be x. So the base of the rectangle will be the entire distance, which is pi, minus 2 of those x's. So here we can see that the base of that rectangle is pi minus 2x. The height is a vertical distance, and remember that vertical distances typically come from outputs of functions. So if I plug x into the function, then the y coordinate will be sine of x, and that will therefore be our height. If we think about the constraints on our variables, we can see that we don't get a rectangle if the base is less than 0, and we don't get a rectangle if the height is less than 0. We also are going to run out of rectangle if the base and the height get too large. So if we think about step 3, which is to let y1 be that area function, and we think about step 4, which is to identify the domain of that function, then the domain is going to be the limitations on x. So we need to think about what the smallest x can be and what the largest x can be. If our x gets really, really small, then that means the point is moving down toward the x-axis. So the rectangle is going to be getting shorter and shorter and shorter. And if x goes all the way to 0, that height turns into 0. So we end up getting no rectangle. So that means 0 is the lower limit of our rectangle's x. If we think about getting x big, we're going to get the rectangle taller and taller and taller. And notice that as this x increases, this other side is also going to move closer to that pi over 2. So if x goes all the way to pi over 2, we will get a super skinny triangle, or rectangle, excuse me, that has no width. So the largest that x could be is that pi over 2. Our step 5 is to find the derivative of that area function. The derivative, we will have to do the product rule. So we'll have our first one times the derivative of our second plus the second times the derivative of our first. And we're interested in knowing when that is 0 and when that is undefined. Well, it's never undefined because we have no division by zeros, no radicals, and no logs. But when it's 0 is a little more tricky because solving this by hand is going to be a nightmare and we're not going to do it. So that's why in your steps, when I say you get to use a calculator, we're actually going to go and look at the derivative of this function and we're going to graph it using the domain. So step 6 is we're going to create a sign chart, and that sign chart is going to be for A prime, and on that A prime we're going to put our domain, and then we're going to put the zeros or the critical points or whatever we discover from the graph of A prime. And then finally when we're done we will summarize. So before we can move on this particular one, since I can't see the critical points, we're going to use our calculator. So what I'd like you to do is in y1 go put this area function, in y2 put the derivative of y1, set your window and graph it. Pause your video and do that now. Looking here, we can see in y1 I've put that base times the height, and I'm going to turn off y1 so that I don't graph it. And in y2 I have that derivative of y1 of x with respect to x, and this is what I want to graph because it will give me the sign chart with more information attached. To ensure that I'm looking in the right place, I'm going to set my window so that the x's lowest value is 0 and its upper value is pi over 2, and then I need to see that x-axis. So now if I graph my y2, I'm looking for when it is positive, when it is 0, and when it is undefined. We can see that that derivative is above the x-axis, so we're positive. Then we cross, and then it becomes negative. That means the area function, which is stored in y1, is going to have a maximum value right at this point. So to figure out what that point is, in this case we will do f5, and we want the 0. So lower bound, if you remember, means to the left, and upper bound means to the right. And we can see that we got a 0 at 0.710. So I can come and put this 0.710. The graph was above the x-axis, then below. And I can say that we equal 0 at 0.710. And so there's our critical point. And then we can summarize. We can say A of x is maximized when x equals 0.710 because A is continuous. So here we're using that first derivative test, and A prime changes from positive to negative. Now the issue is that we have not yet answered all of the questions. We've gone through the steps. We have the calculus to justify where we have a max, but we haven't answered what the largest area is, nor have we said what the dimensions are. So when x equals 0.710, the area is, and we need to go find that, the base is, and the height is. So in order to find these values, we're going to use the fact that x can be plugged in to generate the area, and that the base, I can plug that x in and compute the base, and then the height, I can plug the x in to get the height. So if we look at our calculators, we have to be careful that we don't use the rounded value. If we use a rounded value to compute new values, then we compromise our accuracy. So instead, we're going to use the fact that the calculator has now stored this value of x in the calculator's memory until we overwrite it. It it's going to be xc. So on the home screen, I can compute y1 of x alpha c, and that will give me the area. So 1.22 is my area. I can go back then and I can look at my base, which is a pi minus 2 times that x value. So I can do a pi minus 2 times that xc, and I get 1.721, and then it also asks for the height. Well, the height is the sine of that xc, which is 0.652. And now we're done. With example 3, we're given a rectangular sheet that has a perimeter of 36 centimeters, and its dimensions are x centimeters wide and y centimeters high. And then I'm going to roll this paper up into a cylinder. The goal is to find the values of x and y that will maximize the volume of this cylinder. So we have read it completely. We understand what is given and what is wanted. So now we're ready to do step 2. Step 2 is let's build that model. That model should look like the thing we're trying to maximize or minimize, which is the volume, and we want it in terms of a single variable. So we're going to start with the volume of a cylinder, which is the area of the base times the height. Now the goal is to get that in terms of x, and we can't get there unless we can replace r and y with x's. So this is where those intermediate relationships come into play. If we look at the r, that's the radius of this cylinder, and we know that x is the circumference. So I have the circumference is 2 pi r, and that's the same as x. That enables me to isolate r and get it written in terms of x. We also know that the perimeter of the original rectangle is 36. So that comes from 2 x's plus 2 y's. When I use that relationship, I can get that y is 36 minus 2x over 2, or that y is 18 minus x. So in my formula now, I can replace r with x over 2 pi, and I can replace y with 18 minus x. Now, constraints on my variables, I know that x has to be greater than or equal to 0, r has to be greater than or equal to 0, and y has to be greater than or equal to 0. So we're going to use those to help develop the domain when we get to step 4. If we think about step 3 is to go put that v of x in for y1 because we have a calculator available. So I'll let you do that in a second. Next is we need the domain because we want to make sure that we're looking in the right locations for those extreme values. So if I know that x has to be greater than or equal to 0, then we need to think about what the upper limit on x is going to be. The upper limit is going to occur, x will get larger as y gets smaller because we're going to preserve that perimeter. It'll just continue to be 36. So the smallest that y could be is 0. And if I let y equal 0, then I can see that the largest x will be is 18. With step 5, without a calculator, we want to show what the derivative of this v will be so that we can find the critical points, and then we'll use our calculator to support it. So to do that, we probably want to simplify this so that we don't have to do the product rule with the chain rule. If I multiply everything out, we can see that I'll have a pi over a 4 pi squared, so that's going to give me a 1 over a 4 pi. That's going to be the coefficient of everything. Then I'll have an x squared times an 18 and an x squared times a negative x. This will be much easier to take the derivative of. So with step 5, I'm going to do v prime of x is the coefficient left alone times a 36x minus a 3x squared. I need to know when that is 0 and when it's undefined. Well, in this case, it's never undefined, and the zeros we can find on our calculator. Once we use that and our calculators, we will be able to set up a sign chart for the derivative of v. And on that sign chart, we will put the domain and we'll put the critical points and the signs of whether that v prime is above the x-axis or below. Once we're to that step, we're ready to summarize. So let's go to our calculators now, and I would like you to enter y1 is this, y2 is the derivative of y1, and you want the appropriate window. So pause your video and go do that. If we look here, we can see that in y1 I have pi times that radius squared times the height, so I've got the volume. I'm going to turn it off so I don't graph it, and in y2 I have the derivative of that y1, and then we want to ensure that we're looking in the correct location. So we're going to have the domain, which is x is trapped between 0 and 18, and we need to be able to see the x-axis. If I graph now, we are looking for sign charts with more information attached. We can see that we're 0 at 0 if this comes down and crosses. So we're 0 again here, and we see that f prime, or the volume's derivative, was changing from positive to negative, so we get a max, which is what we're looking for. So we can go look for that 0 now, and we're already on the lower bound, which is to the left, and let's go to 15. It's our upper bound, and it looks like we have a 0 at x equals 12. So here I can see that I have x equals 0 and x equals 12 as critical points, and I'm positive prior and negative after. We can see that v will rise and then fall, so we'll have the max at 12, which means we can now write our summary statement in step 7 and say v has a max at x equals 12 because v is continuous and v prime changes from positive to negative. Now we did not answer the question yet, because the question is what values of x and y give the largest volume. So we've got to find x and y. X we know is 12, y we have to go find. So we find that x value, we come up to the relationship between y and x, and we have 18 minus 12. That gives us a 6. Make sure you include the units, and we're done. Our final example, example 4, is asking us to find the volume of the largest right circular cone that can be inscribed in a sphere of radius 3. So in the picture here, we can see that I have a radius of 3, and then I've put a cone inside that sphere. So what I want you to be able to think about is what this cone can do. The base of this cone can move all the way up to here and make a really short, fat cone, or it can go all the way down and make a really tall, skinny cone. So our goal is to represent the volumes of that cone in terms of x. Now I chose to label x as the distance from the center to the base of the cone. And when we do that, that means we're going to have some interesting things going on with the domain. So our first step, which was to read, we've done. Our second step is to now build a model for the thing that we want to maximize or minimize. We're trying to find the largest volume of the cone. So volumes of cones are 1/3 pi r squared times h. And in this case, the r is the radius of the base. So I've put the radius of the base is y here. So currently we have volume is 1/3 pi times the radius, which is y squared, times the height, which if we look at the height of the cone, it has the piece of the sphere, which is 3, and then the x. So if I add those two together, I end up getting the height. Now remember, the goal is to get this in terms of one variable only. So we've got to get y in terms of x. In order to do that, we're going to go look at the relationship between x and y. Because we have a right circular cone, that means the height and the radius are at right angles. So what we really have here is a right triangle, and Pythagorean theorem applies. So we'll have an x squared plus a y squared equals a 3 squared, or a 9. That enables me to solve for y squared, and I could solve even further for y, except that here I have a y squared, so I can just use that 9 minus x squared. Step 3 is I want to go put this into y1. Step 4 is to figure out what the domain is. So the domain requires us to think about what the smallest x can be and what the largest x can be. If we think about this x getting larger, it could go all the way to this bottom, and so it could reach from the center to the edge before we run out of cone, because the cone will get too skinny and it won't be a cone anymore. So that happens when x is 3. So the biggest x can be is positive 3. Now most of the time we are limited by 0 on the bottom, but in this particular case, if x goes to 0, then I just have a cone that's going through the center of the sphere, and we can actually get a whole bunch of cones up here. So how that's going to work is if 3 plus x becomes a number smaller than 3. So that means that if I want to get smaller than 3, then x is going to have to be a negative number. So what x would be that would create a 0 on that cone's height is going to happen when x is negative 3. So x is going to be trapped between negative 3 and 3. Next, our step 5 is we're going to want to graph the derivative of our original v. So that means we need to be able to take the derivative of that function if we want to get points on a free response. We can see here that we have a coefficient of pi over 3 out in front. And then if I distribute, which might make it easier because then I won't have to do the product rule, I can do 27 plus 9x minus 3x squared minus an x cubed. So if I take the derivative of that, I move through the coefficient, leave it alone. The derivative of 27 is 0. The derivative of 9x is 9 minus 6x minus 3x squared. I need that to equal 0 or undefined. We can see that it is never undefined, and zeros we can get when we graph the derivative. I mean, we could factor it if we wanted, but since we have a calculator, we may as well. Once we've done that, then we're ready to do step 6, which is to sketch that sign chart for v prime. V prime, its domain goes from negative 3 to 3, and we're looking for critical values. So now I'd like you to go to your calculator, put v1 into y1, and put v prime into y2. Then set your domain, set your window, and then turn the video back on. Notice here in y1 I have that 1/3 pi times the radius squared times the height. And then in y2 I have the derivative of y1 with respect to x. I'm going to turn off y1 because I just want to graph y2 so that I can see the zeros and the undefines. And notice that I want to look in the correct place, which means I'm going to limit my x min and x max to the domain. If I graph now, I'm looking for when that v prime is above the x-axis, when it's below the x-axis, and when it equals 0. We can see here that y prime, or v prime, excuse me, is above the x-axis. Then it changes from positive to negative at this point. So I have a max on the original volume function here, and I can do my sign chart. So I need to figure out what that 0 is, and it says lower bound and upper bound. We get a 0 occurring when x is 1, and that's the only time. So prior to that it was positive, after v prime was negative. So we can see that we have a max on v at 1. So step 7 is v of x has a max of, since I want to find the volume, we're going to go figure out what that is, when x equals 1, because v of x is continuous. Here's that first derivative test. And v prime changes from positive to negative. So to find out what that max actually is, I'm going to go plug 1 into v or into y1. So on my home screen, I can go y1 of 1 and hit enter, and I see 32 pi over 3. So that's my max.